Okay, so we are trying to do this introductory course without getting too mathematical and so on. So there are limitations on explaining some of the aspects when you try to do this dynamics without any equations, without any math, because there are some nonlinearities which are involved in doing some of these or producing some of these features, but we will manage. Okay, so visiting again this figure, we said excess energy in the deep tropics, warm temperatures, without worrying about hemispheric asymmetries or zonal asymmetries, which are also very critical, which we implied already in the sea surface temperatures. For example, we said in the eastern Pacific around Galapagos, temperatures are very cold, and in the western Pacific they are very warm. Near Australia and New Guinea there are warm waters, corals, and so on. So that's the zonal asymmetry. In fact, we will see that it comes straight out of the Coriolis as well, and I can just give you a hint at this point. If the winds are already tilted by Coriolis and have become, instead of being northerlies or coming from the north, they have become northeasterlies. Instead of southerlies coming from the south, they have become southeasterlies because of Coriolis. They are going to drag the ocean towards the west, right? Ocean water will also experience Coriolis when the winds begin to drag it. What should happen? So the water just to the north of the equator is going to be pushed to the north. Water to the south of the equator is going to be pushed to the south. So water is being pushed away from the equator, and like Moses, water is being parted, which means just like you need air to flow in to fill the rising air, you need water to come up to fill the water that's getting away from the equator. So we will see that that is called divergence, or water flowing away from some region. Also happens in the atmosphere where you have convergence, winds are coming together, and there is a divergence where winds are going away from a place. So we will see that where there is low pressure, there is convergence, there is rising air, typically clouds, rainfall, so bad weather. Where there is divergence, there is high pressure, and air has to also replace the air, the diverging air at the surface. How does that happen? Air comes from above. Okay, so there is subsidence or sinking air, creating a high pressure as well. So all these features are embedded in them, but you have to use your basic concepts to be able to understand all these very simple linear concepts we are adding together. So we mentioned briefly that the rising air is going to hit the tropopause, wants to go poleward. We will see that it wants to go along the longitudinal direction as well, but let's look at now just this so-called zonal mean meridional circulation, which means we have averaged this circulation here along all longitudes and then looking at the meridional cells. So we are looking at the zonal contrast here a little bit, but when we want to look at the cells, we are typically looking at what happens if we zonally average it, because there are so-called zonal asymmetries, which means along the longitude the winds are not the same necessarily, because we have monsoons in the middle, which we will see in a minute, right? So we said the air that is rising and wants to go poleward is going to be tilted to the right or eastward also, and there is also the angular momentum concept in the sense of air parcel going from 1600 kilometers per hour on the equator towards 1400 kilometers per hour. So it acquires a accelerating eastward speed, which concentrates momentum and creates these upper level jets we call jet stream. This is the subtropical jet stream. The more famous one happens here, the so-called polar jet stream that we will see little bit later. Okay, so polar easterlies are easy to understand in terms of flow going out of the high pressure around the North Pole, Coriolis creating that. What's happening in the middle? So we had the trade winds and we had the easterlies, and it turns out that there are lots of details about how this air that wants to continue to go poleward is going to get unstable because it cannot conserve its angular momentum anymore. The eastward speed gets stronger and stronger, and then it begins to break down. So the polar easterlies are going to be met by these mid-latitude westerlies. How does that happen? You can think of it like for our simple course as a gear, a kinematic link that is connecting the Hadley cell to this polar cell. What is the polar cell? So at the surface there are polar easterlies. At some point Coriolis is going to create enough tilt that it's going to meet winds coming from the south, and it's going to rise again. Again it's going to have clouds, expanding air, etc. Again it's going to hit the tropopause and then going again poleward. So you have created air coming out of the poles, hitting some latitude because of Coriolis and other constraints, and rise, hit the tropopause and go back and sink. So you have the polar cell. So the Hadley cell and the polar cell are directly related to the thermal energy Coriolis, and these are called thermally direct cells. So this is obvious that it's trying to move energy north as well, taking energy from here to the north with a little bit of complication. Here this is creating a cell that is related to the cold temperatures and the thermal forcing associated with that, the energy deficit. And these two cells, this terminates around 60 north, this terminates around 30 north. They're going to have to be connected for mass balance and continuity reason by a kinematic cell or a gear. So the sinking air here is diverging away from the so-called horse latitudes. Just like winds go to zero when winds converge, when winds diverge also, there is a minimum wind speed in the middle. So air is sinking and it's diverging. So you see that the westerlies, or they are called westerlies even though they are southwesterlies. They are very strong westerly winds. So they are going to meet the polar easterlies and create the second cell, which is diverging at the horse latitude, converging at these 60 north, and then rising, hitting the tropopause, coming back and completing this cell, which is called the Ferrel Cell. Okay, for our purpose this is enough. Things in real dynamics are a bit more complicated. There are eddies, there are instabilities, there are baroclinic instabilities, and so on and so forth. But just try to get a clear picture of this Hadley cell, polar cell, and Ferrel Cell. Okay, you can look at this in another way here. Same thing now, named northeast and southeast trades. So even if you don't remember the details of the dynamics, remember the Coriolis effect, remember the cells, remember the winds. These are very critical. So northeast and southeast trades converging into the low pressure rainy band, which will be called Intertropical Convergence Zone, or the ITCZ, which you may have heard of. Leads to rising air and diverging and sinking. And then you have the kinematic cell, or the Ferrel cell, which is also called thermally indirect cell. So this is forced thermally directly, this is forced thermally directly, whereas this is like a gear that is connecting the two thermally direct cells. So we have the subtropical jet stream here with high pressure where the air sinks and diverges at the surface, and you have high pressure here because of cold temperatures and energy loss. So you have the polar cell there. So that is the polar front, or the subpolar low. Again, remember, low means rising air, bad weather, rain. Here it'll be storm track, bad weather, rain, snow, and so on. Okay, so equatorial low, polar front or subpolar low, subtropical high, and polar high. So you have two lows and two highs. Okay, and three cells. How easy is that? Okay, so this is a good way to look at the two jet streams. This is the subtropical jet stream, and this is the mid-latitude jet stream. I said polar jet stream because which is not entirely correct, because there is another jet stream that is high in the stratosphere, which is the actual polar jet stream. So let's call this the mid-latitude jet stream. And you can see that both of them wobble, and you can use your Coriolis to say why that is as well. Maybe I will leave it for the next podcast, but it is very interesting how you can take your concept of Coriolis and the fact that Coriolis increases with latitude in both hemispheres, and the rotational tendency also increases with latitude, which means if you displace an air parcel, not only are you changing its vorticity, you are going to create a pull to bring it back to its original vorticity. So we talked about angular momentum conservation. If you don't know the angular momentum concept, then please read up, because I didn't get into the equations here. It's basically when something is moving around an axis, when you're moving linearly, you have momentum, right? Mass times velocity, for example. When you are rotating, you also have what is called angular momentum, which is additional factor. So it's mass times velocity times the distance from the axis of rotation. Okay, it'll be like mvr instead of mv. So that also matters. So you want to conserve vorticity, which changes with latitude, and you want to conserve angular momentum, which you are carrying from one latitude to another. So those things add up to all the dynamics, including hurricanes, cyclones, eddies, storms, cyclonic flows, anticyclonic flows, and so on. Okay,